Okay, so we're starting topic 9, which is interpolation. So in the lab for interpolation, we're going to be focusing on linear interpolation. And then in Cody coursework, you're going to adjust the algorithm that you write to apply it to other types of interpolation. So do make sure that your lab 9 is correct before you do the Cody coursework. So so let's just talk a little bit about what interpolation is. Okay, the idea of interpolation is that you have, it's typically the case is that you've collected a set of data at some instance. So let's say that you collected them at every 1 minute or something like that. And so you have both the frequency that you collected the data, and then you also have the value of the data. And the way you want to think about interpolation is that you use it when you need something that's in between the data that is available. So for example, let's say that I wanted to know what this value is here, but I don't have data at that location. What interpolation would do and what linear interpolation does is say, okay, well, there's 2 points on either side of it. Let's connect those 2 points with a linear line, and then let's approximate that data point on that linear line between the 2 points. And this type of interpolation is probably the most common, but there are others that are used for sort of very specific sets of data that there might be a better way to do it, particularly if maybe you're looking at time, and so it makes more sense to always use the one before it or something, because time doesn't, necessarily work quite the same as space. But the important thing is that it's used to make predictions. So the outcome or the output of an interpolation calculation is an approximation. And it's an approximation from a set of data that is assumed to be exact. And typically the interpolation uses some sort of analytic function to approximate the point in between the two exact data points. We used to do in this class, we used to do curve fitting because it's something that a lot of people are familiar with from using Excel in their lab classes. And I think it's probably the one thing that people confuse the most is curve fitting and interpolation when they're two totally different kind of things. So curve fitting is when you have a bunch of data, and the kind of idea is that data perhaps has a lot of error associated with it through how it was collected or experimental procedures or whatever. And the idea is that you want to be able to know the trend of the data, and so curve fitting fits an analytic function to the data. Where interpolation is where the data is precise enough that you're looking for information between the data. So the most frequent use of this in at least in your coursework is in thermodynamics, you'll have to use interpolation for almost every single problem that you do in thermodynamics because thermo uses tables. So if you want to know what the density is at a particular temperature, you have to go look it up in a table, but never is the exact temperature, there in the table, and so you're always interpolating between the two. So having an algorithm that does it, or just using MATLAB to do that, is actually super useful, where almost everyone, I would bet 95% of students are still just doing that calculation every single time. Not even using a formula in their calculator, but just redoing that calculation.
Is there like a certain number of points that you need to interpolate properly, or like for like curve fitting, if you don't have enough points, it'll just do the best match of whatever's there. But so interpolation is just going between 2 points that you know are almost perfect.
So linear interpolation uses 2 points because in order to get a linear line, you have to have 2 points, right? So if you want higher order interpolation, then you just use more points. So if you wanted to incorporate curvature into this approximation by using 3 points, then that would be a quadratic interpolation. And if you look, you guys are going to use the interpolation functions in your pre-lab, and you'll see that they have all those programmed in the intrinsic function, higher order ones. But yeah, we are focusing the lab on linear interpolation. However, the point of this assignment is really the algorithm for interpolation, which has nothing to do with any particular type of interpolation. It's used in all interpolation. But let me first just get you the formula for linear interpolation, see where you get it. And so linear interpolation requires 2 points, right? So you need to find the 2 nearest points, the points that bracket the point that you're looking for, in order to start linear interpolation. And I'm going to talk about that when we talk about the actual algorithm. For now, I just want you to know, given that you have these 2 points, what formula do you use to get the start point in between? So what you're doing is you're always looking for the y value, and for some reason, when people start using the intrinsic function, they just mix up all of the different things, because you have the x data and the y data that you're interpolating from. You have the x star, which is what it's usually called, the interpolated x value that you're looking for, and then you have your y star. Those are all inputs and outputs even to the intrinsic function, and you have to have those sorted out in order to be able to even use the intrinsic function properly. And here I'm talking about just 1 point, so 1 x star value that's between any x1 and x2. So I'm going to draw out what you have here. So the first requirement is that you've already found the bracketing points, which means that the particular x star value that you're looking at is between the two. And then you have to know the function values associated with those bracketing points. And with those 5 knowns, you can solve for the 6th one, which would be the y star value. So graphically, what you do is you connect the 2 points with a linear line, and then you locate the y position on the graph. So using either just point slope method, if you remember that, or similar triangles, whatever is familiar to you, you know that you can find that 6th unknown. So similar triangles is usually, I think, one of the easier ones to remember, which is that you can see that there's two triangles here, a little triangle and a big triangle, and they both have the same angles associated with them, so they're similar. So that means the ratio of all of their sides should be the same. So like this side here is y2 minus y1, and this side here is going to be y star minus y1, right? And then this one here is going to be x2 minus x1, and then this side here is x star minus x1. So similar triangles is really straightforward. It just sets those two ratios equal to each other. So the one way you could think about it is if you do opposite over adjacent, which one is that with SOHCAHTOA? Opposite over adjacent. So yeah, tangent. So that means that opposite over adjacent of this one should equal opposite over adjacent of this one because they both equal tangent of the same angle, right? So if we do that, we're going to get opposite over adjacent for the smaller triangle equals opposite over adjacent of the bigger triangle. And here you see you have a relationship with the 5 knowns with the 1 unknown. So you can just solve for the unknown, and that's what linear interpolation gives you. And this is the same formula that's given in all of your engineering classes which use interpolation. So this calculation is just done by hand whenever it's needed. You can also arrive at the same formula by just using the point slope formula and the 2 points that you're looking for. Okay, so this is fine. This is the linear interpolation formula, and this is not hard to program. This is something that we could do after topic 1, right? If we knew 5 things and we needed to find one calculation from those 5 things, we could do that. That's not what you're doing in this lab. In this lab, you're writing the algorithm that is able to basically locate the x and y that bracket, or the 2 points that bracket the point you're looking for. So let's talk about that. So this type of interpolation algorithm is used everywhere in engineering modeling and in any sort of lab work. And the idea is that if you have collected data well, I'll just give an example. If you've collected data like every 2 seconds, but the calculation that you're doing or the analysis that you're doing requires you to know the information at every 1 second, it would make no sense to go through and do each of those points individually, right? So you'd want an algorithm that's able to do it automatically. And that one is even easy because there's a pattern to it. But imagine that there wasn't, and it was just you needed to go from one frequency to a totally different one, even non-uniform frequency. That's what you want this algorithm to do. And I'm going to write out the algorithm for you. So it'll be like the first couple steps of that last page of the pre-lab. And then you can move forward to write the pseudocode and write your code. So this is the idea. And you're going to have to draw this out in order to understand the data that you're actually interpolating in the lab. It's very similar to this in that you're interpolating data that is in time. So there was data collected for solar radiation, and you're needing to interpolate it from hours to minutes. So you're going to have a lot of points. So you have both these dot points, which were collected, and you need to adjust it to get it on those star points. And so you always want to think of stars as the points you're looking for, and the dots is what you were already given. So you guys have any questions about that? So the idea of the algorithm is that it's able to shift the grid, if you want to think about it as a grid, that the data is on. So the name of this is called the window interpolation algorithm.
Would you be able to get a point below 2?
No, and that's called extrapolation. And so again, if you were able to use a couple points on the right side, you could also do that, but it would be a different formula. It's not the same as the interpolation formula. But you could also incorporate the endpoints into your window interpolation algorithm in order to just locate where it is. But this particular algorithm for this lab won't do that. I mean, some people probably did it, but you would have to add extra if statements in there. Okay, so I have an example that I'm going to use for this window interpolation algorithm so that we can actually do some calculations as we're working through it. And it's really, really stupid example. I came up with it for an interview that I was doing. I had to do like a lecture at the interview, and what I'm looking at is a set of data that is the age of an individual compared to the number of texts that they send and receive per month. And so, for example, there's a 19-year-old piece of data who sent 2,317 texts per month. And so the idea is, could we approximate or estimate someone's age or someone's number of texts based off of their age using this data? And I wanted to do this particularly because I wanted to show that the data doesn't need to be in even intervals. It is in your lab, and it is in all the examples I've shown you so far, but it does not have to be. So here's some ages, and then here are some texts. And I'll do these calculations in MATLAB to show you kind of like a quick way that you could do that as well. Okay, so the idea is let's say you had an X star. So remember, X is number of texts. So you have another set of data that has various numbers of texts, and you want to approximate for each of these number of texts the age of the person based off of the data that's given. So let's go through the steps that you would take and start thinking about this algorithm. Okay, so the first thing that you need for this algorithm and you want to think about for your algorithm, and this is always the first step anytime I'm showing you how to write out these algorithms, is that you need your data. So you need to get your x, your y, and your x star. In your lab, you're writing this using a function. So you need to write an interpolation function that uses the window interpolation algorithm and linear interpolation, and it should be able to receive any x, y, and x star and output a y star. So for you, these are going to be inputs. They shouldn't be defined hard-coded in the function. Okay. So before we start actually looking for bracketing points with x star, what should we do with this data? Yeah, we need to sort it. And what do you want to sort by, x or y? Well, you're given x star values, right? So you know that 151 is the first x star, you're looking for a y star. So do you want x and y to be sorted with x or y? Yeah. You want it sorted by x because that's the bracket that you're looking for. So even though in the past this has been an algorithm that I've had the students write, for this lab you can just use the intrinsic sorting algorithm. But a sorting algorithm is a really fun algorithm to write. Okay, now you're just going to start with 1. That's how I always have you think about this. So you want to start by looking at your first x star. And the first thing that you need to do with the first x star is you need to find the window, right? So you need to find the window where the 2 points that are in the linear interpolation formula are on either side of the x star. And if you remember just from the that linear equation, that if either of them are equal to, it also works. So you can put equal to there as well. So then, once you know x1 and x2, remember you'll also know y1 and y2 because you've sorted the algorithm, so they'll just be at the same location. Then you will predict y star using the formula that we already came up with. So that would be here. Some people like to, because this is eventually going to be in a loop, which we'll get to, some people like to have this in to like directly use the indexes in this formula, and some people like to create other variables because it's easier to see what the formula is. So let's see here. How do we do a find algorithm? Have we done any of those before?
What are we trying to find again?
The window.
Oh, yeah, find greater than, less than, for that value that we want.
Yeah, so I don't know if the find function works. For this one, it's much easier to not use it and to just use it the other ways we've done it, which is a for loop with an if statement, right? And then that would be like how you did that planets lab, where you're just looping through all of the elements, and then the if statement will include the condition that you're looking for. Or using a while loop, where the while loop will stop once that condition is met as well. So either of them will do the same thing.
So how would you find the closest with the loop? Because wouldn't you just say like for I greater than?
For the while loop, you mean? Or for either?
For either.
So
wouldn't it just find greater than or less than your x star, but you want the closest greater than and closest less than?
no, because you're going to go through them by neighbors. So this isn't going to say x1 and x2, it's going to say xi and xi plus 1. So you're just going to be comparing neighbors, and once it finds that, is in between two neighbors, which it will only be once if it's sorted, then the if statement will be true, and it shouldn't be true any other time. This is easy. This is just a definition. There's a lot of indexing with all this, so it's not, you have to be really careful with all that. But other than that, that's the whole thing for finding the window. And then, what do you have to do? So that was just how you do it for one x star value, right? Now you need to repeat everything you just did in 3 for all the x star values. So when you see repeat, you want to think loop, right? And what kind of loop would this be, for or a while? Yep, you have to know how many x star values, so for loop is all you need. So this is, I'm going to write this up here. So this is all going to be in your own function. And so once you finish finding all the y star values, you need to somehow report back what the y star value is. So for a function, that's just going to be an output. So you can already kind of see the structure of the function. There's going to be 3 inputs, 1 output. There's going to be 2 for loops nested within each other with an if statement inside. And then the rest you have to figure out is the indexing and how that all works. So let's just try this with a couple examples to see if we can go through and actually run through the algorithm. So let's start with the first x star value, which was 151. And we want to find the associated y star value. So the first thing we need to do is go up here, and we have our x, y, and x star, so this needs to be sorted, right? So we'll just do that by hand really quick. So we want to sort by x, so the smallest x, so it's confusing because this feels like an x, but this is the y. So the smallest x is 49, right? Oh, I think I wrote that data wrong. This should be 61. And then 961.
Probably the one above.
Oh yeah, these are opposite. I wrote these in the opposite in my notes. Okay. So the smallest is 100 then?
Yep.
And then 421. And then what? 961. 1475. 1866. Okay. Oh, one more. Okay, so once you get that sorted, and there's a sort function, it's called sort, but the only tricky part of using the sort function is that you have to make sure that you sort the y the same that you sorted the x, right? So if you get them all sorted just like I did, I had to also match up the right y with it, which, is that in the pre-lab this time? Did I do sort in the pre-lab? Can't remember. I think it was in the data analysis pre-lab, but it's pretty straightforward to use. So let's see. Once you get it sorted, you need to pick your your first x star, which is 151, and find the 2 bracketing points. So the way that the algorithm is going to work in the same as yours is you're going to go to every 2. Is it between these 2? It is. If it wasn't, it would just keep checking until it was. So it's going to use the first 2 points, right? So it's x1 and y1 are the first point, and it's x2 and y2 are the second point. If you were doing this in the loop, you could create variables that were exactly x1, y1, x2, y2, and then just use those in the formula. Or you can just write the if statement in terms of xi and xi plus 1 and then put those into the formula directly in order to eliminate variables. If you plug those into the formula, you get about 73.5. You want to double check that that number is between, because it's linear interpolation, that number must be between the 2 y values or something is incorrect, which it is. In your guys' case, when you write yours, you're going to want to check that graphically by plotting the original data and then plotting the interpolated data on top of it, and all the interpolated data should be in between that. So let's move over to MATLAB really quick. And I wanted to show you a couple of things that you can do if you'd like to make this algorithm a little bit easier. The first thing is you could write a function that receives all the inputs that you need. So remember, there's 5 unknowns. The 2 points, the x and y's of the 2 points, and then the x star that you're looking for, and then the output is the y star. And then you could put your formula, your linear interpolation formula, as the only thing inside the function. And again, this is one where I see people overusing parentheses. So typically a big problem, or a bug that we look for a long time, is just where the error is in this formula. But I'm going to save this, and I'm going to use it first to just check what we just did. Okay, so I put in x1, y1, x2, y2, and x star was 151. And then the output will just give me that value. It's only one line, so you don't need to put it in a separate function, but I see this as kind of like a useful thing that you could just use for other things, so having it in a function is kind of nice. But the idea is that then when you write your actual function, which is going to have, I forget what I do tell you what to call the function. It's going to have a very similar set of inputs and outputs. It's going to have an entire x array. It's all x's, all y's, and all x stars. So these now are arrays, where this was just given that you had the exact points already. And then it's going to output the y star, which is also an array. And here you're going to do your sort. And then, as we talked about, you're going to have a for loop, an if statement, and then you have to do a bunch of indexing to figure it out. And then once you get into this if statement, you're ready to approximate your y star value. You can just call this function that you wrote, define y star. So the y, I don't know, however you end up indexing it, is just going to equal, and then you just insert in each of those like that. And then you could put all these in the same function. This function can go underneath it. So the alternative would be to just directly put in that formula. So the formula, I'm not going to write out the whole thing, but it would, you know, these would definitely be different indexes. Let me change that so that you don't refer back to this and get confused. Because one loop is going to loop through y's, one's going to loop through y stars, so they'll have different indexes. Yeah, so you can just put this whole thing that I just showed you in the function, that can all go right into the loop as well, and then you just have one function. So you can choose how you want to do that. So the structure of your code is going to have this, which can operate independently for any set of data. And then above this, you're going to have lab 9. This is where you're going to import your data. This is where you're going to call this function up here. You're going to call the intrinsic function to make sure yours is working correctly. You're going to do all your plotting all up here. So I'll just write that here so you have it. And then load the data. And the data is in an Excel spreadsheet, so you can easily view what it looks like. But it is not like a huge one like it was in that other lab, so it's not, you don't have to do anything special with making it speed up. Okay, so what I like to always show, I usually do this in lab, but I'll do it now, is how this data works, because very confusing when you actually have to apply this. So you have, or I'll actually write it out, so it's solar radiation, and it's coming in 2 different spreadsheets. So solar, I don't remember what I called the, it's okay. Let me look actually. Solar DNI. So there's minute and solar. DNI is just like the unit for the reading. Okay. So what you'll see in this data, they're both spreadsheets. This data has 2 columns. It has the columns of time and then the reading. And so for this one, it's like every hour, and then it has the reading in the second column. The minute data is a little bit more confusing. Let me tell you exactly what it is. So it has 3 columns. There's a lot more than this. I'm just drawing some of them. So this one was collected every minute, but the first time it was collected was at 4:39. And then it was collected at 4:40, and then it was collected at 4:41. So this is what you need to import in and what you need to use. So this here is your X array, and this is your Y array. And then this here is your X star array. So the idea in general is that you want to interpolate this data that's at every hour, you want to interpolate it to every minute. Okay, that's what you generally want to do. But in order to be able to compare it to actual minute data to just see what it looks like, so you can see the difference between like approximating it versus reading it actually through a reading, I wanted you to use the exact same Y star as is available in this spreadsheet. So the spreadsheet here has mixed units, where this one has hours, and they all need to have the same units, right? You can't interpolate one thing that's in feet to another thing that's in inches. You have to have them in the same units because you're finding the bracket. You wouldn't be able to do that unless they were in the same units. So when you read this file in here, this is going to be like, let's say this is called data. This would be, if you called the whole thing when you read in data, this would be data : 1, this would be data : 2, and this would be data : 3, right? These would be the 3 columns of what you read in. So what I would recommend is that you just use the units of hours, and so you just convert this to hours. So it'll just be the first column plus the second divided by 60. And that way x star is in the same units as x. And then you can just use them for plotting and everything all the same. And so what I would recommend for the lab is the first thing you do is you read in the data and you plot it. You plot the hourly data and then the minute data. Get that plotted. After you finish that, I would apply the data to the intrinsic function. So the intrinsic function is going to give you back the y star value, plot it. And that's actually the whole assignment, is to get the minute, the hour, and then the interpolated, so you can look at the difference between all of them. Then you're going to write your window interpolation algorithm. Once you get it written and called, then you're just going to replace what you had from the intrinsic function with your function. So that's kind of like the process I would take. And you might want, in between just calling your function with this real data, you might want to like make up some data that's easier to tell if it's correct, or something like that. There's some nice ones in the pre-lab, I think, that you can use for that. And that's pretty much it. Do you guys have any questions? Okay, that should be good then.